Okay, I think we can start. Welcome everyone. So we have parallel session 11 now. We have a very diverse line of speakers right now, starting with a little bit about the solar perspective in terms of its outlook, but also this very interesting modeling based on GIS and identifying solar potentials. Then we're going to move on a little bit, understanding the role of bio in ancillary services, which is, I think, a very new dimension that's not very explored much lately, but that's interesting to have in the lineup. And then we have from Aarhus this talk about hydropower and relationship with climate effects, which is also something that is overlooked, I think, and definitely worth to get better. And then we have the water energy nexus, that's last talk that also is related to a little bit these effects in climate. So great to have you all. I'll be chairing the session. Thanks for the emails and coordination. And I can start. So I'm a senior researcher at NTNU, and I work in the Open Entrance project that was mentioned today in the plenary in our sessions. Yeah. So now we start with our colleagues at Exeter. Let me stop sharing my screen, and I let now we have Jean-François.
Yes, thanks. It says that screen sharing is disabled for now. I think you need to allow me.
Yeah.
Yes, you need to make Jean-François co-host.
Yeah. Yeah, this is.
Oh wait, I can.
Yeah.
Right.
Because I gave you the host rights now.
Okay.
Yeah.
So take over. Okay, it should work now.
Yeah. So John, yeah, the floor is yours. Thank you.
Okay.
Yeah, we can see it. Great.
Is this working fine? Yeah. Okay.
Yes.
Okay.
Loud
thank you.
And clear.
Yeah. Thanks very much. Thanks for the intro, and thanks for organizing. And great to see the crowd. I presented at EMP-E, I think 2 years back. Last time I did it, I missed unfortunately last year, but it's great to see the conference happening. I take no credit for this. This is all the work of Femke, who is with us. Unfortunately, COVID has disabled her speech, and so she couldn't say, couldn't present, but she's there. So if there are any questions, then in any case, she's there with us. So this work we did in collaboration with UCL. Now, I want to challenge everybody in this audience with a bold title: Is a solar future inevitable? And you'll see, it's just the data, right? It's an interesting transformation we're witnessing, and I'm not going to present my results as definite. I'm going to say, well, challenge everybody to see, is that what's coming? Okay, so some of you might know the E3ME model, the E3ME FTT model, which is used very frequently at the European Commission and various governments and institutions. It's an energy economy, sort of macroeconomy and environment climate model. In fact, there's a climate model integrated. And the key thing in this model is the interaction between the technology and the macroeconomics and the sort of energy demand. It's quite a well integrated model. It's based, it's a community model based between different institutions, including Cambridge Econometrics, who some of you might know, University of Exeter and other colleagues. In short, it's a highly disaggregated macroeconomic model that's got 70 regions, 43 sectors, And it's especially good in Europe. And in fact, in Europe, it's 70 sectors. It's Eurostat data, super detailed. And there's a family of evolutionary models of technological change called FTT, something I created some 10 years back. The FTT power, transport, heat, steel, but here I'm talking about FTT power. Okay, so the key thing in the evolution of technology is this interaction between costs and deployment. So there's learning by doing, as you know, is making costs decline really, really rapidly in solar at the moment, and all the renewables, in fact, all the new technologies, the old technologies don't really have costs that change very much. Coal electricity is based on, the cost is really a matter of fuel costs, of operational expenditures that aren't really changing, but the capex of solar and wind, as you know, is really declining quickly, such that now we're on the edge where it's breaking the break-even point, really. So what do we see? So that's the basis of our model, really. Now, so here's the learning curve. You'll have seen that before. I mean, solar is, as usual, breaking grounds, but now it's breaking the sort of competitive grounds. If you look at the left, there's all the projections of the IEA over the last few years have been consistently wrong, one after the other. And it's perhaps natural, it's hard to predict the behavior of technology. And on the right, you've got some floor costs that had been included in the integrated assessment models by many, many groups, thinking solar could never become as cheap as it has. And indeed it has. So what do we do? But nevertheless, it's difficult to predict because there's issues of intermittency that may cause problems for solar to diffuse. So what we did is this. I mean, look at the data. We took the most recent data we could get from BNEF, Bloomberg that is, and the IEA over capacity factors, capex, opex, cost of capital, and so on, and put that together in this model that has a learning curve that feeds the diffusion, that feeds the learning curve, that feeds the diffusion, right? And what we get is this sort of situation where we used to think we'd have a lot of coal, a lot of gas, a lot of hydro, and some slowly diffusing. Oh, sorry, the years are missing, but it ends in 2060. Sorry, I've created this graph too quickly. It starts today and it ends in 2060. So we used to think there'd be lots of gas, lots of coal, some nuclear, some gradual diffusion of solar and wind, and that's sort of 2019 baseline of the IEA, I think it was, for the standard sort of new policy scenario. But now our modeling tells us what's on the right, which is a boom, solar comes in, and that's with the new data. So what does that mean? So that's because solar extends its learning a little bit and breaks the grounds, the cost grounds, breaks even with every other technology, really. And then the question is, what happens to fossil fuel-based electricity generation, really? And of course, there could be other policies to have more biomass and CCS, which is not quite as competitive. I mean, nothing can catch up with solar. So we see in different regions, solar really takes over effectively a large fraction of markets. This is what the model says. This is not reality. Of course, I wanted to challenge everybody to see, is this reality though? I mean, is this coming, or is there something we're doing wrong? And here the share of solar for different parts of Europe, it could be very large, but of course, immediately every one of you as energy systems modelers will say, no, it's not possible because there's intermittency issues. So that's the key problem. And that was the reason why everybody was including floor costs in their modeling in the IAMs, the integrated assessment models. So, okay, so what are these barriers? So I guess in the end, the question of whether solar takes over power markets really is about the barriers. And if we ended up finding that there weren't barriers, I suppose what I'm saying could be true. But do we know this? And I suppose this is the direction of research right now. So what are these issues? So we might have issues scaling up so quickly as the model suggests, right? So are we able to churn out these solar panels so quickly? And there may be issues with scaling that across the world in the global south, for example. Are the supply chains able to cope with that? Of course, everything's produced in China at the moment. There used to be production in Europe, the US. Perhaps the production of solar panels will come back to Europe and the US. Perhaps it has to. Do we have the skilled labor available? Is there going to be competition on land? And I think some of the speakers might speak to that later. What's the actual real potential for solar? But I think most crucially, is the finance going to be available? And especially in countries where typically it's difficult to finance large-scale projects because they are seen as too risky. If you think of parts of the global south or Africa, or even some parts of Europe have really different costs of capital compared to, say, Germany or the UK. It's interesting that solar took off really in countries where it's not that sunny, like the UK and Germany. And of course, there are countries where it should really take off, where it's much sunnier, but there are issues of finance. And but then lastly, and perhaps really importantly, what happens to storage? How is that going to be managed? And I guess that we have that in the model, but there's many options we can put in the model to decide what's going to be happening, or how can we envisage the future unfolding. So, of course, if we assume that the cost of balancing the grid was added to the cost of solar as we conceptualize an investor, what we see is that solar might in the end go backwards and cross the competitiveness threshold back above coal again, just because there's so much investment to do in electricity storage. So that's one possibility. Or is the grid and the government going to cover for that, given that we have climate policies and we want to achieve certain targets? Then perhaps that's not the investor in solar that has to cover these costs. And of course, is the balancing done by natural gas, in which case we end up with some sort of gas lock-in, or is the balancing done by batteries or more pumped storage? That's a bit of an unknown at the moment, and perhaps some of the speakers can speak to that later. And of course, there's learning by doing in the storage solutions. And if there's a hydrogen economy where we store a lot of energy in the form of hydrogen that then gets used in other applications such as steel making, that's another option. So yeah, just to conclude then, just to stick to my 10 minutes. So without further policies, solar could really be the largest power source globally. But the question is, what's going to block it from becoming so, if anything? And that could be that there's scale-up issues with supply chains. Can we produce so many solar panels? Investment might be difficult to achieve in different parts of the world. And the energy storage challenges and costs may cut that short or prevent solar from reaching those levels. But that's it. That's my talk. Thank you.
Thank you. Thank you. Nice, really nice outlook and presentation from Exeter, from Femke and Jean-Francois. Thank you. Is there any questions or points of discussion? Something I wanted to raise up, and that because I when I did my PhD, I was doing my PhD on batteries. And back then, batteries was like, okay, nobody's gonna invest in batteries. It's just crazy. But there's been a couple of studies saying how batteries is gonna decline, and it's the same as solar. All the battery studies in terms of the amount of cost per capacity, the projection has been totally off and has gone up much quicker than estimated. And I feel that there's been a parallel story of solar, or nobody thought that solar is going to go so quickly, and now battery is doing the same thing. But you mentioned in your last slide about that is still a challenge, that storage is not competitive enough to be a dancing partner of solar.
Well, I think that you're right. Absolutely. I mean, the story of batteries is similar to the story of solar PV. It's got a similar learning curve, 20%, I think, learning rate, or 22% something, super fast, and it's driven by mobility at the moment, cars. So, and the huge investment in deployment for cars means that then the batteries become available for power generation applications. And that's a big question, isn't it? So can we balance such huge amounts of electricity in the grid using batteries? And if the costs become as small as this learning curve suggests, then probably. I suppose technically for us, we need to implement that in the model, really. The battery learning curve alongside the PV learning curve. And then probably our model is going to say that, yes, we can have all this solar. And again, it's going to be remaining a question. I don't want to be too, making bold claims too strongly here, but I think it's definitely looking like that. That's what appears to be on the horizon. Yeah,
I think that's a nice discussion and points that we see very, very strong parallels. But let's see if these parallels converge in a story. Okay, there's any other questions, or I think this was a really interesting presentation. I really like it. Thank you again. Now we're gonna move on to our next speaker from the Central European University. And the talk is about estimation of future solar energy supply for European buildings using a case-based model. So I please Gergely Molnar, if you can share your screen and your video feed, then the floor will be yours. Are you? Yeah, you are. Please, you are a co-host now. You should be able to share the screen.
Very much. Okay.
Yeah, we can see the screen. Perfect.
Yeah, very good. So thank you for the opportunity, and thank you for organizing this very fantastic conference. In my presentation today, I will talk about the technical potential of PV electricity supply for European building by using a GIS-based model. We all know that there is a very huge threatening of climate change today. We have to keep the global warming well below. We have to decarbonize the energy system by 2050. It is very crucial to decarbonize the building sector as well, because this sector is responsible for 40% of final energy use and 46% of CO2 emission in the EU. In decarbonizing the building sector, the solar technology can play and has to play a vital role. The solar energy, as all we know, is an easily harnessable and predictable form of energy. It has a developed technology, and as a result, it has a continuously enhancing electric efficiency and decreasing prices of the solar panels. Recently, about 5% of the total electricity demand is supplied by PV power generation in the EU, and presumably it will increase in the forthcoming decades. According to a new research, about 1 to 5% of the total land will be covered by solar panels by 2050. In the meantime, 90% of the European building rooftops are unused. Therefore, the rooftop installed solar potentials can not only reduce this competition for the land resources, but also have an enormous potential to increase the share of clean electricity generation. In order to explore this amount of technical potential of PV electricity generation, we explored the building integrated solar energy model. This BISE model was designed for calculating energy production by rooftop PV and PVT panels. This model was implemented in Python programming language and in PyJS environment. It is a global model with a special focus on the European Union. It is a long-term modeling period with very fine hourly temporal resolution, and it calculates the technical potential for 2 main building types and separates 8 building subcategories. Here you can see the modeling logic of the BISC, in which 3 input parameters are separated. Namely, there are parameters or inputs for meteorological inputs, and there are roof-related and different technology-related inputs as well. Starting with the meteorological ones, the global radiation, top of atmosphere radiation, air temperature and wind speed are fed into the model, and they are sourced from different analyses and climate databases. And these inputs are then converted to such radiation components as reflected, direct, or diffuse radiation. And also, it's very important input is the temperature-dependent electric efficiency of the tilted PV panel. The core of this model is a module that is created for estimating the total and the rooftop availability. It is based on different geospatial databases and assumptions taken from the literature. This data is then pre-processed with different GIS techniques in order to get the total roof area for every relevant regions and countries. Afterwards, the total roof area in the model is converted and reduced with the so-called utilization factor to have that area which is suitable for PV panel installation. And this utilization factor includes the aggregated effects of the orientation of buildings, the service area, tilting, shading, and obstacles, and its effects. And its effects on the roof area availability. The utilization factor and the share of buildings with flat and pitched roofs are very important inputs, and they are determined also with the GIS technique in this model. We have a long modeling period, therefore we have to make projections for the roof area availability, which happens in the function of total floor area forecasts and roof to floor ratios for different building types and building subcategories. The technology related parameters in the model is updated from confirmed numbers from datasheets of major solar panel manufacturers. We made 2 assumptions. The first is only the most developed PV and PVT prototypes are considered, and we neglect degradation and technological progress of PV panels during the simulation period. In this analysis, the maximum 3 prototype was selected for the calculation. This PV panel has very high, it's very efficient, it is very high electric efficiency. It is nearly 30%, and its maximum power is 400 watts. In the remaining part of the presentation, I will focus on the results regarding the available building rooftop area and the technical potential of PV production of the EU member states. Malta, Luxembourg, and Cyprus were neglected from the analysis, and despite the Brexit, the UK was included in it. As you can see in the figure on the left hand side, for the starting year of the modeling period, the total roof area was predicted to be 6 billion square meters, indicating its highest values for Germany, for France, and for the UK, while the lowest one was simulated for the Baltic countries, for Latvia or Estonia. Until 2060, an increasing trend of available rooftop area was simulated with an annual growth of 1.1% in each year. And however, it is not shown in this figure, but the steepest increase was projected for the commercial building categories. As a result of the strong correlation between the roof area availability and the technical potential of PV electricity generation, the largest technical potentials were also found for Germany, France, and for the UK and Italy, of course, and the lowest for Estonia and Latvia for the same reason. Interestingly, for Italy and Spain in general, the Mediterranean countries, here the share of the technical potential was predicted to be slightly higher. As you can see, than it would be expected from the share of the available roof area. This is because in these countries the annual radiation income is high, and it is made some compensation on the roof area availability. By 2015, the technical potential may increase, at least according to the simulation in all member states, and there is no change is expected in the rankings. So Germany and France can still remain in the first position in this regard. If we take a look at the first 6 countries in terms of the technical potential for PV electricity production, we can observe an increasing trend by 2015 in all cases. With these dashed lines, we indicated the solar PV electricity production in 2050. And if we compare these reference values with the modeled technical potentials, we can see that there is still a huge untapped potential that can range between 95%, for example, for Italy, Spain, or even Germany, and can be above 95%, for example, for France and Poland. In the Paris Agreement compatible scenario, it is stated that the electricity production by PVs should be 2.5 petawatt hours by 2050 to reach the climate goals and climate neutrality. As we can observe, according to these results, we received a slightly lower PV technical potential by this crucial date, which is 2.16 petawatt hours, which means that the rooftop PVs could be and should be completed also with ground-based PVs in order to reach this 2.5 threshold. If we analyze the problem from the side of building types, for example, at tall commercial buildings, for which the technical potential, for example, for office buildings, where the technical potential was predicted to be increasing the highest pace. For these buildings, the vertical surfaces has much more potential much more installation potential than the rooftops. For this reason, it means that maybe our models slightly underestimated the real technical potential, and by installing building integrated PVs or other advanced technologies on the building facades, for example, solar window or curtain wall, this gap could be reduced further in this case. Yeah, I think I'm run out of the time, so I will skip the summary part. So at this point, I would like to thank you for your attention. Thank you.
Thank you. Thank you. Really nice study and really nice also outlook of PB. So we have some questions from the audience now. We can see in the chat 2 questions that you can read. One question is about can you show us results at seasonal or hourly resolution for each of the EU member states?
Yeah, so actually, these are very new, brand new results. But we have seasonal and even daily profiles for different regions, of course. But for the European countries, these profiles hasn't been analyzed. But based on our earlier results, I can say that the highest monthly profile or highest monthly potential can happen in late spring, for example, in May, and in early autumn. And this is because the temperature dependency of the PV efficiency.
Yeah.
So if there's very high radiation, very high surface or cell temperature, the efficiency drops.
And the second question says about
thermal production.
Yes, solar thermal production.
Yeah, so especially for countries that are really close to the, so they are in lower latitudes, like near the equator.
Oh, but I think the question is whether you consider solar thermal.
Yeah.
Yes, you consider.
I mean, later we will consider it, but right now we just concentrate on the PVs, not on the PVTs.
Yeah. Yeah, and then there is more questions. One question I think is already answered, but what is spatial resolution of the model, which is at the city level, I think, right?
No, because of the meteorological and the climate data, we should use a little more coarse resolution, which is 100 kilometers. But for Europe, our plan is to use an alternate solution. Like there are meteorological analysis databases is very fine. I mean, in 10-kilometer resolution. So our next step is to use this much finer input data.
Yeah.
And of course, in this case, we can have a more reliable.
And then the next question is about which source did you use to collect information about the buildings? For example, height, area, and occupancy. Was it only from OSM?
Yeah, maybe it is referring to the OpenStreetMap. Yeah, so we used so we combined this processing method from many sources. For the building footprints, we derived it from from the global settlement layer. Of course, we use the building cadastrals, and also for some territories lidar data, which is very fine, nearly centimeter resolution data. So maybe it can be extended in the future.
Yeah, thanks. And I think just to everyone, I think the last speaker in today's session has some technical problems, so we have slightly more buffer time now. So I will try not to push too much, but that's why I'm slightly taking more time now to answer, to go through the questions, because they're very good questions. So I'll go to the next question. So that's from Fei Wu, which is going to be our next speaker. She's asking, how's the seasonal fluctuation of rooftop PV? Can we have that at NUTS level 3?
Yeah, maybe I've in part to talk about this seasonal fluctuation. Yeah. So again, the maximum, based on our earlier analysis, the maximum we received in May and in September within the year.
Yeah.
And I can see a question about Spain.
Yeah, last question. Yeah.
Yeah. So we compared our results with the literature, and we realized that for some reason the roof area availability was underestimated for Spain. So we are working on it, and we try to introduce new LIDAR data to correct this problem.
Yeah. Okay, there's no more questions or other points, because the next two talks we will slightly diverge out of solar, which I think has been very interesting, two talks. I can see there's no more questions. Okay, so as I said, the last speaker had some technical problems, and then that sort of has freed up more time for all of us to be a bit more relaxed on the time schedule. And yeah, so yeah, there's one more question. This goes to Fremke and to Jean-Francois, that Patrick asked about, that very surprised about the low forecast for production from wind. And I think I agree a little bit with that. There's other studies that show that wind levels similar to solar.
That's a question. Yeah, I mean, that's what the brute model tells you, if you let it, if you like. But in short, the answer is the learning curve for solar goes down so quickly. The learning curve for wind goes down quickly, but not as quickly. The rate is slightly lower, so there's a divergence. And at some point, the solar cost becomes much lower than wind. They face similar intermittency challenges, so that they end up competing with one another when there's less and less capacity to steal from the fossil fuel technologies. So when the fossil fuel technologies become quite small, it starts to get dominated increasingly by the renewables, and that's where you've got a competition. I mean, ultimately, I guess that countries like the UK would keep investing in offshore, as well as Germany, Denmark, to keep it really competitive. And I admit that potentially we underestimate the cost reductions in offshore wind, as well as the deployment rates. So potentially wind could take, but it will never take as big as a space as solar. So I admit sort of the uncertainties, but solar will dominate as far as we can see.
Thank you. Now we can move slightly out of solar and move to other renewables and other aspects of renewables. I'll let Fei Wu to share the screen and welcome her to her talk. Her talk is titled Balancing Intermittency with Ancillary Bioenergy, which is something super relevant. I think balancing and ancillary services are a key for the integration of more renewables. So, yeah, all yours, Haywood.
Yes, thank you. Thank you so much. That's very interesting discussion about the solar and rooftop PV. And now we will switch a little bit into the role of ancillary bioenergy. And just a brief introduction about myself. I'm Faye. I'm currently a PhD candidate at ETH Zurich. And I'm presenting my recent work together with Dr. Adlia Müller from the Institute of Organic Agriculture in Switzerland and Professor Stefan Finninger from TU Delft. And we would like to look at the role of ancillary bioenergy in a 100% renewable European energy system in 2050. So first of all, I guess we all have the same question, what is ancillary bioenergy? Probably for many of you, it's the first time you will see it in the literature. That also the same situation for me half a year ago before I started this project, because from the current research we have higher and higher sustainability standard about biomass, about bioenergy. We have go even deeper into that category, that even those energy crops, the short rotated forests that can meet strict sustainability criteria by the EU, they will still inevitably cause land use conflicts, food competition. So contrary to that concept, we would like to introduce ancillary bioenergy, that is the energy from non-dedicated biomass, not from energy crops, not from short rotated forests, but only from residues, waste, and byproducts, co-products of little or no value. In this way, we can provide the land use conflicts of food competition. So that will leave us to this green area of ancillary bioenergy. However, the idea is brilliant, but the problem is always about data. About ancillary biomass, it has been fragmentedly studied in the literature, mainly for the current or historical potential. Some look at the co-products, some look at more types of residue, because for most of the energy model right now, we only have, say, straws made like 3 or 4 types of major agricultural residues, but we have more untyped minor agricultural residues available. But how to get those data? So our gap and motivation here is that we don't have ready to use 2050 ancillary bioenergy potential data, and for different biomass feedstock, how do we pair them to the proper conversion technologies? I mean, we can use forest biomass for gasification, but we cannot use the manure from coals for gasification, right? There should be some optimal pairation between feedstock and technologies. So here come our research question. The first is the basis of our work is how much ancillary bioenergy will be available. And second, based on the potential data, we'll be able to see how to optimize these very different and limited AB among competing demand in a 100% renewable and European energy system. In that way, we would like to fill in the gap that currently we don't have a clear future role of bioenergy in EU policy. We don't have a breakdown target of bioenergy in the new RED II directive by EU. And we also have contentious sustainability issue about bioenergy, that some major energy scenarios, they don't include bioenergy at all in their 2050 scenarios. And most of the scenarios right now, they only focus on the power source only. And what will happen when we have a sector coupled optimization model to look at the role of bioenergy? So to achieve that, our methodology is first to get the untapped potential of ancillary bioenergy. We would like to use the first fuel system model called SOM. It is a material flow model, and we would like to extract 100 more types of agriculture commodities from false data in 2050. And we also identified those very valuable byproducts with high energy density, say those byproducts of animal fats that could be used to produce aviation fuels in the form of kerosene. And in that way, we will be able to fill in the gap of those untapped potential of ancillary bioenergy that we know they are here, but they are not part of our data set right now. And based on that, we will feed in our AB potential data right into the energy system optimization model called Eureka LIPE. As some of you may have already heard the brilliant talk by Dr. Bryn Pickering yesterday. It's a sector-coupled energy system optimization model. We are doing linear optimization to see what will be the scenario under the least system cost. And to achieve our goal, we will have a sector-coupled demand from power, heat, transportation, and industry. Our temporary solution is based on hourly demand profile, and we are looking at 35 European countries. So in our reference scenario for 2050, here are our two major assumptions. First of all, in the green box, it's related to our supply potential for AB. We assume for the agriculture system, we don't change the current structure, we don't change the numbers of livestock or crop production, and we ensure that we have sufficient nutrients circle and to ensure we have soil fertility. So in say, we don't change the current structure of the agriculture system. And based on that, we will pair different ancillary biomass to the proper energy conversion tax. And in our energy model, we assume every country, they have self-sufficiency, which means they will only meet their own demand of biofuels using their own domestic biomass supply. And we are using our 2050 technology cost estimation from DEA, Danish Energy Agency, like most of the models do. And to assume like in our reference scenarios, we don't use any gas storage or CCS. So to answer our first research question, how much AB will be available in our scenario? Surprisingly, we will have quite enough AB, even if we screen out those dedicated energy crops, those short rotated forests compared to the major, those mainstream scenarios and the current situation. In our modeling results, the lowest sustainable potential, that is when we apply very strict sustainability standards to ensure we have sufficient nitrogen cycles, we will still have the very decent number around 1,700 kilowatt hour, which is slightly above the current final consumption of the whole Europe. And breaking down by different types, we will see we actually have very different spatial distribution of different ancillary bioenergy feedstock, which means when we aggregated them by similar properties, so that we can use that for the same energy conversion technologies, we will have this unbalanced spatial distribution. Say in Nordic region, we have very high potential of forest residues, but do they have also a high demand for that? So that will lead us to our next research question, how to optimize our limited AB among competing demand. So first of all, it's about the spatial distribution, as we have mentioned before. So if we can see the map by country in our 2050 reference scenarios, ancillary bioenergy will have an average utilization rate. That is, we divide the actual utilization by its total potential and get this percentage number. It's around 65%, not that low, but we will expect a lower distribution pattern in southern region in Europe, probably due to the less heating demand in our scenario. And what about the end use by sectors? If we compare our modeling results in 2050 to the current situation in the whole Europe, we will see the major AB will be used for industry fuels and heat. They will constitute over 90% compared to the current situation that was mainly used for electricity and transportation. It is because that for the industrial fuels, they are not so easy to be replaced by other renewable fuels, by other renewable power to X technologies. So in that sense, the model thinks it's better to use the cheaper biomass feedstock to provide the same amount of industrial fuels required by every country. That's a decent result, but we are greedy, right? We want to increase our utilization of the AB. So what if we add more infrastructure, say we enabled Europe to have a networking transporting system that we can move biomass feedstock and biofuels around to meet the European demand with all the feedstock available in every country. And the result is quite satisfying, as we can see. If we compare this dashed line, that is our reference scenario without any infrastructure, and we compare that to our additional infrastructure, if we introduce the methane gas storage, or we introduce the transporting network between neighboring countries, we will see that in each cases, as long as we have transporting network, we will have a higher utilization rate of AB, around 40% in every scenarios. So that's the key to enhancing AB utilization and reduce the system cost in any cases. And for the gas storage infrastructure, if we introduce the underground methane storage, we can have cheaper methane around 30% to 50% in our 2050 scenarios. However, this will not make such a difference to the total system cost. You can see any numbers below 1 is lower than the default scenarios, and those go beyond 1 is higher than the default scenarios. So all in all, to wrap up my presentation today, here are 3 major take-home messages we think are key to our recent work. So in our 2050 optimized scenario for ancillary bioenergy, first of all, it's about the potential. We will have around this number of kilowatt hour of AB in 2050, and the average utilization rate is quite decent, around 50% to 65% without any land use or food competition. And for the major consumption sectors, as industrial fuels, especially for methanol and heat, they will not so easily be replaced by other renewables. So that will make the most sense to use our ancillary bioenergy in these 2 sectors in a sector-coupled, fully renewable energy system. And finally, if we would like to increase the utilization of AB, it's reasonable to deploy more additional infrastructure, say the methane storage and the transportation network. They could, especially when we combine them together, they can well enhance our AB utilization and reduce either the system cost and methane cost in all sense. That's all for my presentation today. If you have any questions, comments, or you're looking for some collaborations, just feel free to reach out to me through email, or we can chat in Zoom or later. I guess I will stop sharing right now.
Thank you. Thank you. Really nice presentation and really nice perspective on of the role of bioenergy, biomass in providing balancing services, and also the utilization part, because I think this utilization part sometimes is overlooked. Some models, capacity expansion models, pick up some flexibility sources, and then the model, of course, use them. But when you look at the utilization factor, or that's very low. So of course, there's no business for this. But here, a good point is to demonstrate that you can reach really high utilization factor, and then that makes it not only interesting, but also plausible business-wise, that it's not going to be an balancing that is not very used. And then, yeah, very, 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 very nice. So maybe there's some questions, anyone that has overall. that would like to raise anyone? No, maybe I have a more basic question, because you call it ancillary bioenergy, and I think that is, at least for me, is not a very familiar term. So could you elaborate a bit more on that?
Thank you for the question. It's also our motivation to present at EMP-E, because it's kind of the first time in the literature we would like to bring this new concept, because we realize for the current potential, the bioenergy people are trying to identify all those untapped potential of bioenergy we are not using right now, but in a fragmented way, but they can be combined together. So that's why we would like to combine not only the residue, the waste, and also the byproducts and co-products together, and define it as ancillary bioenergy. And to make that concept more clear, we can look at the upset of the story, because currently we are relying mainly on the dedicated biomass. Say we assign a certain area of agricultural land, probably they are of marginal value, to grow energy crops, mass cancers, or we have a certain area of low ecosystem services. We use that for short rotation forests. They perfectly fit in the current sustainable standard of EU. But one major problem is that in our model right now, it is so hard to capture the indirect land use change and the corresponding carbon emissions inside that land use change, because as long as we use those land areas especially for bioenergy, we will have land use change. So one way to get over that is to use ancillary bioenergy, because we are reusing, or in a circular economy manner, we are using what is left to be waste, or they're just of very little value. However, we are not using all of them, as the collection fees or the transportation fees, they also count for the energy system. So by doing so, we identify those byproducts, co-products with high energy density, say animal fats or the shears from almonds or walnuts. So it will be a waste to just dump them into some kind of waste energy to just burn them. Instead, we would like to reuse those ancillary bioenergy in a way to make the best use of the energy content inside. Thank you.
Okay, that's a nice explanation, because then you are also linking this highly to the circular economy, a little bit concepts that that is that's very very new, really nice results. I think I like this, that for me the two main highlights is this point about the utilization factor, this new concept of ancillary bioenergy, and the third point is that you also showed its connection to sectors, specifically industry, which industry has, a really crazy amount of way to go for decarbonize, and then and this was also something I will highlight more.
Yeah, exactly. Thank you so much for the question. I'm not sure whether I have already used up my time.
I think we can now go to Denmark. Let's go to Denmark. We have next talked by Ebbe Kilgotke. Sorry if I'm mispronounced your name. We're going to talk a bit more about this effect of climate into hydropower operations, which at least that's what I understand from the talk title. Ebbe, the floor is yours.
All right, thank you for the presentation, Pedro. I hope you can hear me all right and see my screen.
We see everything.
Okay, great. All right. So as you mentioned, my name is Ebbe Gutske, and I'm a PhD student at Aarhus University. I'm from the Department of Mechanical Engineering, and I'm one of the energy system modelers. I will present the research of mine, which will cover how you can model hydropower in the European energy system when accounting for two factors. One is the penetration of high share of renewable, such as wind and solar, and second, how climate change might potentially impact the future resource that we can dispatch for electricity production. So to start out, why do we bother about hydropower? It's currently providing approximately 15% of the electricity generation in Europe. It's what we call a dispatchable generator, which means it can provide extra flexibility to the electricity grid, which is highly attractive when we go through the green transition and increase shares of wind or solar or both. And so I question how can we rely on this resource in the future. First of all, I will split it into two and start looking at how what is actually needed by the electricity grid to what is needed from hydropower to balance the intermittency from solar and wind generation. And second, I will see how the supply might be altered in the future when accounting for climate change projections from existing climate models, to ask the question: are we actually able to meet such a requirement from the first box? Yeah, so I will briefly explain my method that I used to describe the first question, and then I will emphasize a little bit more on the climate modeling part. To answer how the green transition impacts or might likely impact hydropower, I am looking at this paper, which was published last year. It was made by Marta Victoria, and it uses the energy system model that I also use. We use it in our research group. It's called PIPESA-EURSEC, Python for Power System Analysis for Europe, using sector coupling of the electricity and heating sector. On your right, you can see her results of the electricity mix after having decarbonized the energy system in 2050, and it has a high share of solar and wind capacities. So what I do here is that I extract I acquire the time series of the modeled hydropower dispatch and compare it with the historical electricity generation, which I collect from the ENTSO-E transparency platform. So if we look at Norway and Spain, you can see here that the green line represents the modeled hydropower generation in a decarbonized energy system. And you can see that for both Norway and Spain, this energy system model that we use, which uses cost optimization to minimize system costs, we experience this higher seasonality of the dispatch, being high winter and low in summer due to a high share of solar generation. So yeah, this is just a short recap of my approach for answering this first question, and then I will move on to answering how is the potential actually for the hydro resource. Yes, and that's illustrated by this flowchart here. So we want to answer how is the climate change impacting hydropower. And we compare two different climate periods. One is the beginning of the century and the other is end of the century, each consisting of 30 years of sample. And the signal that we are investigating is inflow, so how much water is fed into the reservoirs. And this is modeled using the runoff variable that we acquire from the climate model that we are considering. The runoff is essentially the excess water that is neither absorbed by the soil or evaporated into the atmosphere. Second, we use a database illustrating the delineation of the watersheds to determine the upstream areas, and then we aggregate the runoff on a country level. And that's, if we move on to the next slide. Yeah, so we'll not only consider only one climate model, but we'll consider an ensemble of climate models. That's what I illustrate here. We have 5 different global climate models, or general circulation models, as they are also known as, and 2 regional climate models. And each of them has 3 different emissions scenarios, ending up at 24 climate projections. This is then converted into inflow, as I also illustrated with the flowchart. We have the location of the hydropower plants in Europe from this database from the European Commission Joint Research Center. And then we use the climate model from the Eurocortex to aggregate the area, which we call the upstream area, and aggregate inflow on a country level. And then we'll have the same matrix with the inflow for 22 countries. And then, since we're dealing with the climate model, we know that it's biased, and we have to correct it. We have to bias correct the results that we obtain, and that's what I illustrate here. For each country, we have a historical inflow, mainly collected from the Ancillary transparency platform, and that is used to obtain these monthly correction factors that we'll have to use for our projections. Then the way we assess climate models, then the way we assess climate change is by looking at the ensemble of our climate models. That's illustrated here by the distributions. The blue represent the beginning of the century, and the yellow the end of the century. And then we compare the mean value of each of them to indicate the change in annual inflow due to climate change. And this is also where we do statistically significant test using 5% significance level. And when we look at the results, we obtain a data set for 22 countries in Europe. If we look at the map here, the heat map that illustrates the change in annual inflow at the end of the century compared to the beginning of the century. And that's for some of the countries, you can see the seasonal profile for the inflow at those 2 periods. If we zoom in on 3 of the countries, Norway, Spain, and Austria, we can see, first of all, that for Norway, we have an increased inflow during the winter period and less during summer. If we look at the results from the energy system model, we can see that it's actually favorable for the system to have a higher winter dispatch, which means that the inflow increase in winter from climate change is actually, in this case, would help the system. Historically, we could also see that for Norway, since it has high storage capacities, it actually has an anti-correlation between the dispatch and inflow. On the other hand, Austria, if we look at that, it has a summer peak, first of all, in the inflow. And historically, it has also had a peak in the electricity production during this same period. And that can be described by the historical correlation between the inflow and dispatch due to low storage capacities. So that's why it's not necessarily feasible for Austria to meet this requirement of, to some extent, a higher winter dispatch. And for Spain, we can see generally that it has throughout the year less resources for hydropower production. So, so the conclusions are, first of all, that the increased seasonality from the energy model is observed. Furthermore, we can also see higher ramps of the dispatch, which I've not included any figures of due to time limitation. Second of all, are we able to meet such requirements? That depend on which countries we are considering, since it has a very latitude-dependent impact on the inflow. Second of all, we would also it will also depend on the actual current storage capacity and the seasonality of inflow and dispatch. We have also made an analysis of the combined effect of these two parameters, and it has shown that the system would need to compensate by increasing the wind and solar power capacity. So if you're interested in reading more about this, we have published this paper 1 month ago, approximately, in iScience, and yeah, that is actually what I had to present for you today.
Thank you. Thank you. Really state-of-the-art presentation on a really nice paper. I think now we can have some minutes for questions. We have good timing before the conference closes in 15 minutes. So I had a question about, yeah, you showed this a bit, these new patterns occurring in Spain, Austria, Norway, and that okay, it's changing a little bit the amount of hydro capacity and so on, but also we're gonna have new patterns in terms of demand, given these climate inducted scenarios, and also we're gonna have a new power mix because of solar and wind. So how do you think that this is it positive or negative towards hydro? Of course, overall we can discuss about what does it mean, but how that affects to hydro overall.
Yeah, so that's a good question, and that's also one of the limitations of the study, that we have assumed that the demand is not going to be impacted. Of course, that would be interesting to include a more realistic situation where we have higher, I mean, of course, you could say in this study we are coupling the electricity and the heating. Definitely we would have changed demand pattern. Maybe you could say that on average the air temperature increases due to climate change, so the winter demand would not be as large as it is in our data set. That's just an intuition. Apart from that,
also the summer is going to be hotter, so there's going to be more need for cooling.
Exactly. Yeah. Of course. Yeah. That's probably the most important thing. Yeah. That during summer, you would have a higher demand, and what this I mean, it's actually quite consistent that the results they suggest that the summer hydropower resource is reduced. So so it's not that reliable in summer, but in winter it might be that it has a higher share.
Yeah. Yeah, this is that's interesting scientific question about understanding this overall effect into hydro, I think it's going to be probably hotter summers and then cooling. Also a strong solar PV, as we see in the earliest presentation. Yeah, I think there's many factors to consider, and also another point, but of course this is not really related to your research, but a little bit related to the previous presentation in terms of this capacity factor, this utilization factor of hydro. So at least some of the models we have run here in Norway, and we see that this utilization factor goes down a little bit, because there's so much solar or other technologies that are ahead in the marginal cost, of course. Yeah, this is another, let's say, I don't know what to say, a challenge or opportunity for hydro, but that another factor that influences its long-term. This utilization in 2050 is not the same as it's happening today, meaning that if utilization goes down, as we have seen in my models, then meaning that it's less profitable, even though it's a green technology. I just trying to connect the presentations and ideas on that.
Yeah, you're right. Yeah, definitely. It's an interesting point. Yeah.
Yeah. So I don't see no questions from the audience. Yeah, I think if anyone wants to raise up any other questions or any other points from every presentation or the previous presentation, also from Fei Wu, any questions? Okay, so I just have one last question. In the ancillary bioenergy, did you guys consider any cost sensitivities in terms of investing or developing this technology into the modern Calliope, for example, and whether this was competitive enough with other balancing technologies like batteries, for example, or yeah, that's because it has to be competitive enough that it beats batteries, for example, or hydrogen if it becomes cheaper enough. I don't think that's the case, but that's probably a difficult assumption to make in a new concept technology.
That's a very good question, actually. And for the cost related to ancillary bioenergy, I would say there are two major points. Since we are taking advantage of these almost free feedstock, so the normal, fee we need to pay for get those traditional biomass, they don't exist. However, the major cost is related to the logistics, the supply chain, because we need to collect those tiny little potential, this untapped one into our energy plants or CHP, something like that. So what we have done now is quite preliminary. I didn't put it on slides because we only have 10 minutes, is that we test the different costs of supply chain from JRC. So we have the tracks only routes, and we also have track plus trail different routes, and we define the cost as in per ton per kilometer based on our neighboring country networking system. So we will have higher costs where we would like to travel longer distance and for heavier bio feedstock. And by applying those two more different supply chain, we don't have a very high difference in terms of the total utilization rate of ancillary biomass, but we will have slightly difference in the total system cost because if the supply chain is slightly cheaper than our default scenarios, then the model will choose to transport as much as possible to balance the whole European continent using the potential from every country. And if the supply chain is slightly higher in terms of cost, then the model will choose to say for those countries who is already abandoned in feedstock, it's better to just supply yourself with your country instead of do exports to other country. But the total difference in terms of different supply chain does not vary a lot. Yes, I hope this could answer the question.
Yeah, this is what I was thinking also, this supply chain, the logistics behind. And no, but this answers very well that this could be a major weakness if a reviewer of that can pick up, but I think you have some reasoning there. Yeah, thanks. And any, I can see there's no questions in the chat, but I think we deserve all of a break, 5 minutes before the conference closes. I have to say we had a very strong lineup of presentations in this session, really strong, really motivational and really good. So thanks for the effort and thanks for the very strong presentations today. So I guess you guys can stretch your legs and go for a coffee and then see you at the closing session in 6 minutes. Yeah, so thank you, Eve, thank you, Faye, and thank you, Jean-Francois, and thank you, Gergely. Thank you for your time.
Thank you for sharing. See you.
Thank you, everyone.
Ciao.
Thank you, Pedro,
Ciao.
for moderating. Bye.
Bye-bye.
Bye-bye.